Basically, P1 on CK, beautiful space, but it's got some problems. It's one thing, it's not compact, as I've mentioned several times, or even locally compact. Also, as I've mentioned several times, it's totally disconnected. Now, one of the key things you do in complex dynamics, which is what a lot of the subject of non-archimedean dynamics is motivated on, is you talk about not just points in the two set, but components of the two set, that is connected components. Well, if you're dealing with a totally disconnected set, the component is going to be a point, so there's not really much point in doing that. Now, there are some sort of hacky ways to get around that, let me talk about a nicer way, which is that there is this space called the Berkovich projective line that is topologically much nicer. It's a compactification of P1 of CK. So it contains P1 of CK as a subspace, and it's compact, and it's still Hausdorff. But even more importantly for our purposes today, it's not only it's path connected. Okay, so it's a really nice space topologically. You might not like it so much in the next 5 minutes, but trust me, this is really the way to do it. Okay, so to talk about it, to define it officially, let me start with the Gauss norm and restricted power series. So this ring up here is often called, denoted this way with the double angle brackets. In the lecture notes, I mostly call it the script A bar of 0, 1 to suggest the disk of the closed disk, closed unit disk. So what it is, it's just simply the set of all power series, formal power series in C, defined with CK that converge on the closed unit disk. And equivalently, by that fun fact at the beginning of the previous lecture, that's the same as saying that the limit of the coefficient is 0. So it's just a ring of power series that converge on the closed unit disk, centered if you would. Now it is a ring. That's not immediately obvious, but it's not the word proof. You can put what's called the Gauss norm on this ring. By just simply defining the norm of, and I'm denoting this is denoted various way. I'm going to use zeta of 0, 1. Again, that notation is intentionally supposed to suggest the disk of radius 1 centered at 0. Okay, that's what the zeta of 0, 1 is. And the reason I'm using zeta is because ultimately this is going to be a point, and so this is supposed to suggest like a complex number. So that's why I'm using that wacky notation. But anyhow, the norm of a given power series is just simply the maximum of the absolute values of the coefficients. And that is a well-defined thing because the coefficients are going to 0. So there is actually a finite number of them that contain the maximum. It turns out, this is not obvious, but it's proven in the lecture notes, that is equivalent to defining the norm to simply to be the supremum of all the absolute values of f of x where you let x range through the closed unit disk. Again, we're talking about f as a power series converging on the closed unit disk, so it makes sense to talk about absolute value of f of x. Just take the supremum of all those things. Turns out that supremum is actually attained, so equivalently it's the maximum. Again, I'm whizzing by 10 pages worth of proofs here, but you can take that for granted. That these three things here are all defined and the same. Okay. More generally, a bounded multiplicative semi-norm on this ring of restricted power series. Again, A bar of 0, 1 is just simply the set of all power series that converge on the closed unit disk. So it's a non-negative real valued function, which I will either denote zeta or norm sub zeta, depending on whether I want to think of this as a norm or as a point. So bounded multiplicative semi-norm means these things. The norm of 0 is 0, the norm of 1 is 1, that is the norm of the power series 0 is the real number 0, the norm of the power series 1 is the real number 1. It's multiplicative, it satisfies the triangle inequality, and of course the bounded part means bounded by the Gauss norm. Alright, so it's bounded because the word bounded is because of this last condition, the multiplicative because of this condition. You would think norm because of the other two conditions. What makes it a semi-norm as opposed to a norm here is that what's noticeably missing from these conditions is that we are not requiring the converse of the first thing. That is, it is possible, maybe, for a non-zero power series to have norm 0. So that's why it's a semi-norm as opposed to a norm. Of course, a norm is also going to be a semi-norm, but not conversely. And it's not just a side comment. I said the traditional triangle inequality, but it turns out that you get the non-archimedean one actually for free, given the particular ring we're working over. Again, that's not obvious, but it's true. Okay, so here are some examples of bounded multiplicative semi-norms, which will. So, for example, take any point in the closed unit disk, and again, my closed unit disks are in CK, complete algebraically closed non-archimedean. So we can define a norm associated with point x just simply by the norm of a given power series and just take f of x and take its absolute value. It turns out that that is a bounded multiplicative seminorm. It is definitely a seminorm as opposed to a norm, because, for example, if f were the power series z goes to z minus x, this guy is going to spit out 0 for that guy, even though z minus x is not the 0 power series. So that is definitely a true seminorm as opposed to a norm. More generally than that, if you have any disk contained in the closed unit disk, possibly the closed unit disk itself, you can define a norm associated with that disk as simply the supremum of the absolute value of f of x on that disk. Again, not obvious that this is a norm, but it is. In fact, if you write that disk as either the closed or open disk of radius r centered at A, and if you rewrite a given power series on the closed unit disk as being centered at A, and you can always do that. You can always do that. That is, given a power series on the big disk, and given any smaller disk, you can rewrite the power series as a power series on that smaller disk, centered at the center of the smaller disk. Then the norm associated with D of a given power series F is just simply for these CNs now, the maximum of absolute value of CN R to the M for that radius R. These two things coincide. Again, this is not obvious, takes proof, but it's not that bad. By the way, this hopefully will remind you of a quantity that came up at the previous lecture. In that previous lecture, it was over n bigger than equal to 1. Now I have n bigger than equal to 0. And then it does matter. Let me see. And it turns out that if the disk is a rational closed disk, then that supremum up here is actually attained. If it's not a rational closed disk, if it's rational open or irrational, the supremum may or may not be attained. Usually not. Okay. Let's see. What else do I want to say about that? Okay, so since the open, by the way, please note, it may have not been obvious from this original way of defining it, but from this way of defining the norm, you can see that it doesn't matter whether it was the open disk or the closed disk that you were looking at. You get the same norm both ways. This formula is exactly the same. Right? So it turns out, since those two norms are equal, I'm going to denote that common norm by norms of zeta of A comma R. And I want to point out that if A is 0 and R is 1, that is, if we're talking about the closed unit disk, then this is exactly the Gauss norm. So it's consistent with my earlier notation. Because all these R's here become 1s. So really, when I defined the Gauss norm as the max of the absolute values of CNs, it was really the max of the absolute values of CN times 1 to the n. But I just didn't show you the 1 here. Okay. So the Berkovich unit disk is defined to be the set of all bounded multiplicative seminorms on that power series. Okay, so you can all go home now because now you know what the Berkovich unit disk is. And we equip it with the Gelfand topology, which is the weakest topology, such that for every power series, the map that sends the norm to the norm of that power series on the map is continuous. This definition is approximately as clear as mud. I know that. So anyhow, let's not worry about the topology for the moment. But again, what we've done now is we have this space, this set of points. Each point in the space is itself a seminorm on this ring of power series. And the key thing to keep in mind is, for every point in the original closed unit disk, you get one of these points. But you get some others as well, in particular for every disk that's in there, you get some. So that means this is really meant to suggest the closed unit disk here. So what is in there? Well, as I just said, for every point in the classical closed unit disk, you get a seminorm, and that's a point in the Berkovich space. So that's great. And now for the disks, tend to get separated into two different types for reasons that will hopefully become clear later in the lecture. You have for rational closed disks, or equivalently rational open disks, because it's the same norm. You call the corresponding norms, that is the supremum of the power series on that particular disk. You call those corresponding norms type 2, but if it's an irrational disk, so if its radius is not the absolute value of anything, you call that a type 3 point. And again, it will become clear later why we call those different types. There's also this annoying thing that can happen, which is that it is possible to have, even in a complete field like CK, it is possible to have a decreasing nested chain of disks such that the intersection is empty. If you haven't seen this before, I'm not going to be able to convince you that you have it right now. There's some examples in the lecture notes. If you've seen it before, then yeah, you know this is true. It's just this weird, wacky thing that can happen. At least in a lot of complete algebraically closed non-archimedean. What's going on is most of these fields CK that I'm dealing with are not what's called spherically complete. Spherically complete means anytime you have a decreasing chain like this, there's something in the intersection. So a lot of them are not spherically complete. Although one thing I want to point out, when you have a chain of disks like this, the radius has to be bounded below by a positive constant. That is, so the chain of disks, if the radii actually go to 0, there is necessarily a point in there because it's a complete field. But if the radii don't go to 0, it is possible that the intersection is empty somehow. And now, by the way, what I've written down here is I've correspond each point in here to some sort of geometric object, a point, a rational or irrational closed disk, or technically I need to say an equivalence class of decreasing chain disk and empty intersection, because what I want is there to be each point in here, that is each semi-norm, to be associated with a unique geometric object. So, by the way, there's lots of open disks that share the same rational closed disks, so that's why I'm sticking with rational closed disks. So what I have on this slide is a one-to-one correspondence between geometric objects and points of Berkovich space now. So if the geometric data is different, then the corresponding semi-norms are also different. But you need an appropriate notion of equivalence classes of decreasing chains. It's in the notes, but don't worry about those. The type 4 points for our purposes are not that important. You just need to know that they are actually there. The main ones we want to focus on are the type 1 points that we started with and these disk-like points. All right, so let me try to explain to you now why this Berkovich space, when you throw in all these semi-norms, why this is now a path-connected space. Now, I haven't actually carefully defined the topology, but, well, I guess I did, but I didn't explain it. But still, let me just give you an intuitive argument as to why the space is path-connected. So the idea is, on the left here, I have a kind of diagram I had in the first lecture. So these are like disks sitting inside of your field CK. On the right here, this is a subset of the Berkovich space. And I'm going to try and walk back and forth between them. So in the previous lecture, I said that my disks always have positive radius. And that's true except on this one slide, just to make the argument a little simpler, I'm going to allow disks of radius 0. So I'm going to draw a path between, so I have two type 1 points, that is two classical points, x and y, two elements of the closed unit disk in CK. I'm going to draw a path between them in Berkovich space. So think of x as the disk of radius 0, centered at x. And now increase that through arbitrary disks, closed disks of radius r, centered at 0. So you start with this point, which is the disk of radius 0, grow it as a larger and larger radius disk. And what's happening in the Berkovich space is you started at x and you're moving along this segment here, which consists of disks of radius r, as r varies from 0 up through something else. And it's really, I mean, there's really a subset of the Berkovich space which is actually homeomorphic to a subset of an interval in the real line. It's not just kind of like it, it's homeomorphic to it. Until you get to the radius is the absolute value of x minus y. So that's when you're getting up to the Berkovich point corresponding to this mid-sized disk here. And that's this point right here, zeta of x comma absolute value of x minus y. That is a type 2 point, please note, because its radius, absolute value of x minus y, is the absolute value of something. But it's also, by the way, because you can recenter disks at any point, it's also a disk of the same radius centered at y. So now we can shrink the radius back down, only viewing the center now as at y, passing through arbitrary point zeta of yr, which corresponds to the closed disk of radius r centered at y, until you get down to y. Unless we've drawn a path going from x up to this point, this type 2 point here, and then back down to this point y. Along the way, we're passing through both type 2 and type 3 points along the way. Just as you go along the rational line, as you go along the real line, you pass through both rational and irrational points. Exact same sort of thing. Just for kicks and giggles, I threw in the segment from this disk here up to the full disk. So this is often called the Gauss point, because it corresponds to the Gauss norm. So that's also a segment heading up here as we increase if we were to increase the radius further, which is why that looks Y-shaped. And of course, hopefully you can imagine here, this disk here, I mean, I sort of drew two residue classes within it, but there's, infinitely many residue classes in here. So I actually, if there'd been another point over here, Z or something, I could have shrunk down towards that one, or another point here, W, I could have shrunk down towards that one. So the picture of the whole space is something like this. I can't possibly draw the whole space here, but the idea is you have the Gauss point up at the top, and these are supposed to be the type 1 points at the bottom, and everything in between essentially is the type 2 and 3 points. So essentially, so let me explain the picture. So the idea is that any given type 2 point, like the Gauss point, I have all these different residue classes. And I can pick a point in some such residue class, a type 1 point in some such residue class, and I can shrink my radius of my disk down towards that point. So I guess the idea I'm trying to steer away from, yes, these guys were defined as semi-norms, but I want you to think of them more in terms of their geometric data. Think of them as each point of the Berkovich space as corresponding to a point or corresponding to a disk, or one of these is not just changed to disk. So you can shrink your disk here down to, say, this point right here, smaller and smaller radius. But along the way, you could have decided, no, I want to branch off here and shrink down towards this point. Or you could have gone down a different branch to begin with, etc. And so these points that I've highlighted along the way, these are all type 2 points. Now, of course, along any segment here, I have infinitely many type 2 points. So because the rationals are dense to the reals, basically. So so as I go along here, I mean, I do 3 of these points along here, but there's infinitely many. And at every single one of them, for every element of the residue field, which is infinite, by the way, because we're working over CK, I have a direction I can branch off in for all these different smaller distances I can go. So this is an insane looking space. It's at every one of these type 2 points, which are dense in any segment, I have an infinite amount of branching. And off every one of those branches, I have an infinite amount of branching off infinitely many points. It's just truly crazy. Yeah?
Can you think of the type 4 points?
So I tried to illustrate a type 4 point here. So that although really these things are scattered everywhere. So the idea is here, I started with this disk, and then I got a smaller disk, and then I got a smaller disk, and then I got a smaller disk, and so on, working my way down. But so Matt Baker and Bob Rumley have a book that's coming out in about a month where they do the Berkovich projective line really intensely. And they describe this as being cauterized off at that point. So it's somehow they remember these radii for type 4 points are down below, so it does not make it all the way down to the bottom. But by the way, this kind of thing is happening everywhere, scattered throughout the whole thing. Another comment to make. This is, technically this kind of object is called an R tree. So it's like a tree from graph theory, except you're allowed to do all this infinite branching in a dense collection of points kind of thing going on. Another thing to point out, though, is the topology is not what this picture would seem to suggest. You have to understand how to read this picture. The type 1 points, which in my picture are all at the bottom, are dense in this space. And the reason for that is you have to understand, at this point, I drew 3 branches coming out of it, but there are really infinitely many. And the rule of the game is, and this kind of thing happens a lot when you do things like infinite products and stuff in all different areas of number theory. The rule of the game is, if you want to take an open set containing the Gauss point, or containing any type 2 point, let's say, well, there are infinitely many branches emanating from that point. Any open set containing it has to completely contain everything off all of at most finitely many of the branches. That is to say, if I want an open set containing the Gauss point, I can pick 75 of the branches coming off of the Gauss point that I'm going to say, I'm not going to contain that entire branch. But for all of the infinity minus 75 other branches, I have to contain that entire branch. And certainly most of those branches, well, in fact, all those branches contain type 1 points. So if I take any open set containing the Gauss point, yeah, maybe I omit the 3 branches that I've shown here, but I'm containing all of the others, so I certainly get some type 1 points in there. The type 2 points are also dense, the type 3 points are also dense, the type 4 points are also dense. So at least if there are some. For example, if your value field, value group rather, is the entire interval 0 to infinity, then there are no type 3 points because everything contains the absolute value of something. So I mean, there can, or if you have a spherically complete field, there are no type 4 points. But anyhow, if there are some points in that type, they are dense. That type of force is dense. All right, but I don't care about the disk. I care about, well, I do care about this, but more I care about the Berkovich projective line. So the way you build the Berkovich projective line is you take 2 copies of the Berkovich disk, and you call one have the variable z and the other have the variable w, and you glue them together along w equals 1 over z. So then you glue them along the annulus absolute value z equals 1, appropriately interpreted. So intuitively, what that means is, on the previous slide, I've got branches corresponding to all the residue classes. Well, I just add one more branch corresponding to heading up towards infinity. That's all I'm doing. So this is essentially the same picture, except I've got this one extra branch heading up towards infinity. Otherwise, it's the same picture. I threw in an extra point, an extra type 1 point alpha here just to illustrate the connection. All right, so that's the Berkovich projective line. There are other equivalent constructions of it, but that's the idea to have in mind. Again, think of this thing intuitively. Think of its points. Think of every point. I'm lying a little bit, but every point is either a point or a disk, essentially. Corresponds to a point or disk back in the classical thing, along with these annoying type 4 points that correspond to infinite chains and intersection disks, blah, blah. All right, but within that, I want to make an analog of disks and stuff. So if you give me a point in the one of the classical points and a positive radius, I can talk about the analog of the closed Berkovich disk. So the closed Berkovich disk of radius r centered at A. All right, this is an official definition of it, but again, I want to think about all the points in Berkovich space as their geometric analogs. So it's the set of all of the points in Berkovich space whose corresponding geometric data, that is, a corresponding point, a corresponding disk, a corresponding chain of disks of the intersection, is contained in the original disk in CK. So, so this is just like, and this agrees with my previous definition of the Berkovich unit disk. The Berkovich unit disk consists of all points in d bar of 0, 1, along with all disks that were subsets of d bar of 0, 1, along with all these chains of intersecting disks. Just do that for any disk. Just take all the points, type 1, 2, 3, or 4 in here, whose geometric data is contained in the corresponding disk. And that's what the Berkovich disk is. That makes sense? All right, and similarly, the open Berkovich disk, just one minor technicality here, same kind of thing for the corresponding open disk, except that you do not include the point, the Berkovich point that actually corresponds to that disk itself. Okay, minor technicality, but that's the right thing to do. Which would be an issue if you were talking about an irrational disk for disk. So by the way, please note the now disks of irrational radius, irrational disks are different whether you talk about them being closed or open, because the closed one will contain that point and the open one will not. Okay, so there's now sort of 4 different types of disks: closed, open, closed, and irrational or rational, combined into the way you want. So it turns out, it's maybe not obvious, but in the Galfond topology, the open disks are open and the closed disks are closed. That's nice to know. Even nicer, although at first it might sound weird, I mean, in CK, if you recall, all disks turned out to be both open and closed, as topological says. Here, they are not. And they better not be, because I told you at the beginning that this was going to be a path-connected space, therefore connected. Well, definition of connected is that you do not have any empty, non-empty proper subsets that are both closed and open. So if a set is open, it better not also be closed. So the open disk is open but not closed. The closed disk is closed but not open. By the way, just going back to this, I mean, so the closed disk of radius 1 centered at 0 consists of all of the branches, including this one. I know it's pointing upward, but it's part of the closed disk. Is all of these branches down here, including the Gaussian. The open disk of radius 1 centered at 0 is just the branch heading down towards 0. Well, including all the side branches that come off of it, but not these ones off of here, and not including the Gauss point itself. Okay, so the closed disk is everything down here. The open disk is just everything down here. All right. And now it turns out when you work in P1 of C, the disks form a basis. Well, disks, including disks of infinity, form a basis for the topology. That's not true in Berkovich land. Instead, they form a subbasis. Now, just to remind you what those terms mean, since it might have been a while since you've had undergraduate topology, this has come up. A basis for a topology means a set of open sets such that any open set can be written as a union of those basis opens. A subbasis, or sometimes it's just called a base, although I think that's a little confusing, is a set such that it's not necessarily a basis, but it's more like a generating set for a topology. Equivalently, a subbasis is a set so that if you take all finite intersections of subbasis elements, you get a basis. Okay. So that's but what do you get when you take intersections of these guys? So what I mean by these guys is I mean open disks and complements of closed disks. So to talk about sort of a P1 Berkovich disk, open P1 Berkovich disk should be either an open disk in the usual sense of the complement of a closed disk. So an open connected Berkovich asteroid is the intersection of finitely many open P1 disks, P1 Berkovich disks. So again, take the whole Berkovich space and punch out finitely many closed disks. Or if you like, take an open disk and punch out finitely many closed disks. And what I just said at the bottom of the previous slide.
Closely disconnected metric space.
I'm sorry, I missed the beginning of it.
We were saying constructions work in a closely disconnected metric space.
I don't know. I'm sorry, I just don't know the answer. I'm not sure about general totally disconnected metric spaces. I would imagine not, but I really don't know. Sorry. Let's see. All right, so this what I was saying down here comes down to this theorem that, and this is, I mean, I told you what the Gelfand topology was before, but in practice, at least in my practice, if you want to, the way to understand the Gelfand topology, the topology on the Berkovich space is the basis that you use is Berkovich, open Berkovich connected asteroids. So again, around any type 2 point, that will contain all but finitely many of the branches coming off it. But by the way, even for the branches that you miss, you have to extend at least a little ways into every branch, and you have to completely contain all but finitely many of the branches to be such a thing. Also, Berkovich space is uniquely path connected, which is even stronger than path connected. Again, it's like this tree-like thing. So this is saying not only given any 2 points is there a path between them, and actually, copy that thing actually homeomorphic to the closed unit interval, but there is one and only one subset of the space that is homeomorphic to the closed unit interval having those 2 points as endpoints. And again, that suggests that it looks like this tree thing. There's only one way to get between any 2 points. If you fly American, it doesn't matter where you're going, you have to connect to Dallas. Like that. Anyhow, but another thing you want to do is, given a point, you might want to, we will want to remove that point and see what happens. So if you remove a point of Berkovich space, if you remove a point of type 1 or type 4, these points are sort of at the end of the tree, the leaves of the tree. So if you pluck off the leaf, the rest of the tree is still one piece. Okay, it's one single connected component. If you remove a point of type 2, that's like removing the trunk, and you get thousands of infinitely many branches fall off, and you got now infinitely many components. If you remove a point of type 3, and this is why type 2 and type 3 distinction is made, you've got two. Type 3 point has no branching. You can either make the radius bigger or smaller, but that's the only option you have. So you get 2 components when you remove a type 3 point. And these components that you get are called directions, because they're the directions you can move in away from zeta. So you have infinitely many directions at a type 2 point, 2 at a type 3 point, and 1 at a type 4 or type 1 point. So again, this is what the picture was. You can see that if you remove a type 2 point like zeta of 0, 1 or zeta of 0, alpha, you get all these different pieces. Whereas if you remove a type 1 point like alpha, the rest of the thing is still in one piece. If you remove a type 3 point irrationally along here, you just get the one side and the other side. Okay. All right, so now we actually want to have functions acting on this space. Again, let me give you the totally clear as mud official definition of how a rational function acts on the Berkovich space. So, although I'm not even giving you, I'm even waving my hand a little bit in this official definition, supposedly official definition. So, for any point, take a Berkovich point. So it's a semicolon, right? And given a rational function, you can take the thing that's going to be a seminorm that takes a rational function. Technically, what you need to do here is work with take a rational function, declare its norm to be, take phi after h, and take the zeta norm of that thing. It turns out that is also a seminorm, and therefore it's a point in Berkovich space. So declare phi of the original seminorm zeta to be whatever seminorm you get by whatever that is. I mean, it's like, yeah, you can write down this definition and it works, but what does that mean? So let's actually understand what that means. So if you're dealing with a type 1 point, that is a classical point, a point that's actually in P1 of CK, then phi of it is just exactly what you think. It's a number. Plug it into phi and you get out another number. Okay? And that's what phi of a type 1 point is. So that's easy. Then the obnoxious way to answer the rest of it is to say, well, the type 1 points, as I said, were dense in the Berkshire space. It turns out, it is a black box fact, that that any phi is now defined with type 1 points extends continuously to the entire space, and because they're dense, that extension is unique. So there you go. That's what phi of R2 is. That's not very helpful though. So what's really going on? All right, so that's what the next few slides are about. So let's start with just degree 1 rational maps. So, and I'll just see what they do to the disk-like points. So if you take the disk, the point corresponding to the disk of radius r centered at A, and you hit it with the scale by C map, well, I mean, it just does to it what it does to the disk. It multiplies the center by C, and it multiplies the radius by the absolute value of C. So the corresponding type 2 or type 3 point gets mapped to that other corresponding type 2 or type 3 point. It does what you think it ought to do. And similarly, if you translate, it just translates the disk. So if you started with the disk centered at A of radius r, it gets moved to the disk centered at A plus B. And only the Berkovich points actually gets mapped that way. If you hit it with 1 over z, it's ever so slightly more complicated. But basically, there's two cases. If 0 is not in the disk that you started with, then and you hit that disk with 1 over z, the image of that disk under 1 over z, it's got to be a disk. Remember from the previous thing, if you plug a disk into a rational function, you get a P1 disk. And since 0 is not in this original P1 disk, infinity is not in the output P1 disk. So you actually get a disk. And that's the disk that you get. And the corresponding type 2 or type 3 point that you hit is this guy. I mean, that looks like a mess, but that's just the image of the disk of radius r centered at A under 1 over z. Just that corresponding disk. That's the second line. The top line is perhaps easier to understand, although there's a technicality that's sort of the key to Berkshire space work going on here. So take the disk of, suppose that the disk you started with did contain 0, so you may as well think of it as the disk centered at 0 of radius r. Well, if you hit that with 1 over z, you're going to get the complement of the disk centered at 0 of radius 1 over r, right? Well, that corresponds to the Berkovich point of the centered at 0 of radius 1 over r. So the idea is somehow you have this various geometric data describing points. If you're dealing with a disk, then any open disk, the Gauss point corresponds to the closed unit disk, but it also corresponds to the open unit disk. It also corresponds to the disk of radius 1 centered at 1. It also corresponds to the disk of radius 1 centered at whatever your favorite thing of absolute value 1 is. But it also corresponds to the open disk that's the complement of the closed unit disk somehow. So that's what's going on here. So every P, not just every disk, but every P1 disk corresponds to a unique type 2 or type 3 point. So anyway, I just want to say that. Any linear fractional transformation can be written as a composition of maps of the previous type. So using that, you can figure out what the image of any at least type 2 point is under such a linear fractional transformation. Let me just comment, this is not obvious, but it's a fact, that the Gauss point is mapped to the Gauss, if you're dealing with a linear fractional transformation, that linear fractional transformation maps the Gauss point to the Gauss point if and only if it was actually defined over the ring of integers. That is to say, when you can write it as AZ plus B over CZ plus D, where all the A, B, C, and D have absolute value less or equal to 1. Well, you can always do that. You can always clear denominators. But when you do that, the determinant has absolute value 1. So somehow the idea is these guys map to this form fix the Gauss point, and anybody else actually moves it somewhere else. Any other linear fractional transformation. All right. So what about more general rational functions? Let me just start with, for a more general rational function of higher degree, let's just start with the same question as before. When does it fix the Gauss point? Well, it turns out if you write phi out as a rational function, you may as well clear denominators and assume that all the AIs and BIs are integers, and that you didn't clear too many denominators, so that at least one of them still has absolute value 1. Okay, so you can always do this. And then you can reduce, just take the reduction that is the element of the residue field. By the way, the K bar here is to indicate that that's algebraically closed. It's not the reduction. The bars over here are reductions. Sorry for the double notation. but anyhow, so the point is, all these guys are elements of O, so just take the mod, the maximal ideal, and you now have a rational function with coefficients in the residue field. The thing is, though, you might now have some cancellation. So, for example, maybe this was, by the way, I didn't say this before, but this was supposed to be written in lowest terms. There's nothing to cancel. So maybe, however, A0 and B0, for example, maybe both had absolute value less than 1. Well, when you take them mod the maximal ideal, their reductions are suddenly 0. And so now you can cancel a z from top and bottom. Or maybe other things can happen. Maybe you can cancel a factor of z minus 1. Or maybe now the entire numerator is just a constant multiple of the denominator. The whole thing becomes constant, or something like that. So we might have some cancellation if you don't have any cancellation. That is, if the degree, after you cancel everything, if the degree of the reduced function is still the same as before, we say phi has good reduction. Sorry for stealing the thunder joke. And but if the degree generally is going to be some cancellation. If the degree is still at least 1, it didn't all totally die when we say it has non-constant reduction. Usually, actually, the whole thing totally dies if it has constant reduction. But we'll see that in a second. So it turns out, to answer the question at the top of the slide, phi fixes the Gauss point if and only if it has non-constant reduction. So it might not have good reduction, but if it at least has non-constant reduction, that is the if and only if condition for it to fix the Gauss point. Let me ask you to accept that on the tape. So now at least we can understand. What happens to an arbitrary type. This slide's a little complicated, but it's not as bad as it looks. I'll give you an example on the next slide. In practice, this is very easy to do. So. Hello there. Excellent. Welcome back. Houston, we have a problem. All right, so let's see now. For okay, so let's see. So for any type 2 point, I'm going to try and tell you how to figure out what the image of it is. So first of all, given any type 2 point, you can find a linear fractional transformation, I'll call eta, that moves the type 2 point to the Gauss point. This is easy in the following sense. Any type 2 point is a disk, right? So you can translate to center the disk at 0. And then, because it's type 2, its radius is actually the absolute value. So you just divide by that absolute value, and you have the closed unit disk. So you can always do that. There's more than one way to do that. So now, let's suppose you're given a non-constant rational function and a type 2 point. Let's figure out what phi zeta is. Well, first of all, take theta as the previous line, move zeta to the Gauss. It turns out, and here's another fact I'm going to ask you to accept on stage, that there is always some linear fractional transformation such that if you do theta after phi after eta inverse, you get non-constant reduction. I'll be proving that. See how to deal with it. Okay, so this is a general fact, and I mean, there's nothing special about phi after eta here. If you put any non-constant rational function, there's always a theta here, so that you get non-constant reduction. What that means then is, for whatever that theta is, what is phi of zeta? Well, it's exactly theta inverse of the Gauss point. The reason for that is the following. I mean, if you believe the things I've asked you to believe, I can now actually prove what I've just said in this slide here. Namely, all right, this guy has non-constant reduction. The claim I asked you to believe on the previous slide, that means if we stick the Gauss point into it, we get the Gauss point out of it. So let's stick the Gauss point into it. Well, eta inverse takes that to the point zeta that we're trying to find the image of. So what we have is coming out of eta inverse is zeta. So zeta is what's going into phi, and coming out of phi is phi of zeta, the thing that we're trying to find. So whatever comes out of phi of zeta goes into theta and comes out as the Gauss point, because we said we stuck the Gauss point in, we got the Gauss point out. So theta is taking phi of zeta to the Gauss point. So hit both sides of theta inverse and hit this line right here. Wow. So see what a little faith buys you? Okay. So now, by the way, these choices of eta and theta are not unique, but they're cosets in, now this is the ring of integers here, those are unique. That's related to the fact a couple of slides. All right, so now you understand maybe sort of how rational functions act on the Berkovich projective line. Let me give you an example to hopefully solidify it. All right, so what I have here is, here's Berkovich space. There are a lot of branches coming off of that, but I don't want to draw them. So that's the line for the unique geodesic from 0 to infinity. So we have that. Now this point here, zeta, here's the Gauss point. And I'm looking at this point here, zeta, 0, what can I use, absolute value? Which is somewhere along there. Okay. These are both type 2 points. Now that I care about the Gauss point, that's just for reference. Okay, so I'm plugging it into this function. I intentionally picked a rational function that had a pole smack dab in the middle of the obvious disk that this point corresponds to. If there wasn't a pole in there, I could just take the image of the disk, it would be another disk, and the image Berkovich point would be the obvious, this point corresponding to that image disk. But if I take the image of the image of the disk of radius p, absolute value p centered at 0, it turns out it's the entire p1. So I can't do that. But I can apply the algorithm of the previous slide, which says first find an eta that maps the point I started with to the Gauss point. So the obvious thing to do is just divide by p. So slide this guy up to the Gauss point. Okay. So now I'm supposed to take phi of eta inverse, that is, say phi of pz, which gives me this. Well, if you reduce that mod p, you get z over z, which is 1. So like I said, often when you reduce the thing, you just get a constant after you cancel everything out. Very common thing. But once you see that, you can sort of see, well, hey, if I subtract 1 off the end of this rational function, then that's going to kill the z here, and then I can divide by p, and then maybe some nice stuff will happen. So let's try theta being take z, subtract 1, and divide by p. Well, then if you take theta after phi after eta inverse, so just to compose this thing with theta, you can check easily exactly this thing right here, which when you reduce mod p is not constant. Wow, that is what we're trying to do. There is always a theta, we found it, and the corollary, or the side proposition to that theorem that there is always a theta is, and it's easy to find in practice, and it's not a really hard thing to do. So that tells us, according to the previous slide, that phi of zeta is theta inverse of the Gauss point, which is easily seen to correspond to the disk of, here's 1 here, the disk of radius absolute value of p centered at 1. That's right. Not there, but okay. So all right. So this is how you do it in practice. How you figure out the image of a type 2 point under a rational function. You can just play with this. It's fairly straightforward. Okay. So now we can finally do some dynamics. This is something like the multiplier. Given 2 points, 1 point mapping to the other, at least if they're type 2 points, you can define the local degree or multiplicity to be the degree of this reduced map. So now remember, since zeta maps to C here, by definition, this degree here is at least 1. Okay, that was the definition or whatever, that stuff from the previous slide. We can define the degree at zeta to be this degree, which is at least 1, and it will be at most the degree of phi. So eta and theta are the unique thing, or points to the Gauss point. And if you actually have a periodic point, so phi to the n maps zeta to itself, we say that periodic point is indifferent if this local degree of the iterate is 1 and repelling if it's bigger than or equal to 2. Please note attracting is missing here. Yes, I know that. But by the way, just so you're not misled, repelling points don't actually repel in most directions. There's infinitely many directions to look in, based on remember. They will repel infinitely in at least one of those directions, but not all of them usually. But there is a good reason to call them repelling points. There is also a notion of defining the local degree at type 3 and type 4 points. If you do happen to have a periodic point in one of those types, though, it turns out it's always indifferent. The local degree is always 1. If it's periodic. If it's not periodic, it might be a degree higher than 1. But if it's a periodic point, it has to have an absolute degree 1. All right, so to define Berkovich for 2 and Julia sets, let's not even try to touch epi continuity. Let's just go with the other definition and declare a set to be dynamically stable if, when you take the union of all its iterates, it omits infinite limiting points of Berkovich space. Now, if you remember from the previous talk, I said a point was for 2 if it had a neighborhood, a disk around it. So if you look at the union of all iterates of the disk, you would miss at least 2 points. Let me just go from broken and say omits infinite limiting points. There are good reasons for that. See the lecture notes. So the Berkovich for 2 set is just simply defined to be the set of all points in Berkovich space that have a dynamically stable neighborhood. So the set of all points you can find an open set around it. So let's say an open connected aphoid that is dynamically stable. That when you take the union of all of its iterates, you're missing at least infinite limiting points of the Berkovich space. And the Julia set is simply the complement. So that's the definition. What do these things look like? Well, basic properties, the 2 sets open, the Julia set's closed by definition. And it's not too hard to show that the 2 set of an iterate coincides with the original one. That's the same for the Julia set. And that it's invariant. If you have a point in the Fatu set, its forward image and all of its pre-images are also Fatu, ditto for the Julia set. Conveniently, we have not actually changed anything. So if you take a type 1 point, so the F without the subscript here refers to the classical Fatu set that I was talking about an hour or 2 ago. That is just simply the Berkovich Fatu set intersected with the set of type 1 points. So it's good, we're not talking about something truly different. We're simply extending the Fatu set into the type 2, 3, and 4 points. And similarly for the Julia set. All the attracting points of Fatu, that's just an immediate corollary of the previous line, because any attracting periodic point, there are no attracting periodic points of type 2, 3, or 4. Any attracting periodic point has to be type 1, so it's in this Fatu set, so it's in that Fatu set. There is content to this guy here, though, which is that all repelling points of Julia, because there are repelling points of type 2. And so it does take a little work to show that they are automatically in the Julia set. No matter how small an open connected aphoid you put around it, the union of all its iterates will cover essentially the whole space. Indifferent periodic points of type 2 are a little bit more complicated. Certainly if the residue field is algebraic over a finite field, which is the case like it's FP bar, the algebraic closure of a finite field. Certainly if that's the case, then the indifferent periodic points are always for 2. If not, if the residue field is bigger than that or characteristic 0, you can have indifferent periodic points that can be Julia. There's some condition which is sufficient, I think, but not necessary. There's an if and only if condition, which I don't want to get distracted on. It's not that bad, but let's not worry about that. It's a little too off topic. So let me just compare and contrast all 3 of the spaces. So first I have complex dynamics, then I have, if you do classical non-Archimedean dynamics, so dynamics on the type 1 points, and if you do dynamics on the Berkovich space. So in the complex world, it is an extremely difficult question about whether a different periodic point is the 2 or Julia. In fact, it's still partially open. And even the part that's closed is really, really complicated. Yoko's won a Fields Medal for answering part of it. So that's a very, very, very deep problem, which actually ends up being related to Diophanty approximation. But on the type 1 points, all the indifferent periodic points are for 2. Just boom, automatically. And this is, you can easily check when you take an indifferent periodic points, it's just an exercise in playing with power series. You put a disk around such a, you can find a small enough disk around it that maps into itself. And there you go, you have a dynamically stable neighborhood, because all its iterates will also be inside itself and therefore miss infinitely many points in the rest of Berkovich space. As I said, in Berkovich space, there are sometimes type 2 indifferent points if your residue field is big enough for which you get Julia. But again, that's completely understood. The Julia set in P1 of C is always compact for the stupid reason that it's a closed subset of the Riemann sphere, and the Riemann sphere is compact. And we all learned in undergraduate topology that a closed subset of a compact space is compact. Similarly, the Berkovich Julia set is also compact because it's, I guess I didn't prove this, but I previewed it, that the Berkovich P1 is indeed a compact space. And the Julia set is a closed subset. But for the type 1 points, the example that I didn't do in the last lecture was going to demonstrate that the Julia set need not be compact. So somehow the extra points you need to make a compactification are of type 2, 3, or 4. As Joe mentioned, the Julia set in complex world is always non-empty. It turns out the same is true in the Berkovich world. But as we saw in one example in my first talk, the type 1 Julia set can be empty. For the 2 sets, it's a little different. Again, as Joe mentioned, it is possible to have a complex map with empty for 2 set. This is impossible in either type 1 or Berkovich for 2 sets. And Joe also mentioned something about closure of the set of repelling periodic points. So he mentioned the theorem that the complex Julia set is always the closure of the set of repelling periodic points. The same is true in Berkovich space, which is not obvious, but you need to use both type 1 and type 2 repelling periodic points to do that. To do type 1 points, however, we don't know. So Shah proved the following result, that the Julia set is contained in the closure of a set of all periodic, type 1 periodic points. All of them, attracting, repelling, or indifferent. Bezovan showed that if you have at least one repelling type 1 periodic point, then the type 1 Julia set is equal to the closure of the set of repelling periodic points. So if you have at least one type 1 repelling periodic point, you get yes, you get repelling density in this box here. But it is and whether or not you have that, certainly every point of the Julia set is of type 1 Julia set is in the closure of a set of all repelling of all periodic points. But it is at least conceivable, given what we know. I don't think this can happen, but we can't prove it doesn't. It is conceivable maybe that there is somehow a type 1 Julia set that is non-empty, contains no periodic points at all, and yet every point of it is accumulated on by attracting points that are in the Fatou set. I can't imagine that such a thing happens, but if you can prove that it doesn't, I would be very interested to know. All right, that's all for today. Thank you.
Any question?
Oh, yeah.
Yeah, exactly.